Let's say you're reading a problem out of chapter 12. It's a mixture of ideal gases. And in the problem statement, you're given the mass fractions of each of the constituents. But somewhere in the problem, you realize I'm going to need to determine the partial pressures of each of the constituents for some reason within the problem. And so I need to get the mole fractions because the only way to determine the partial pressure of each constituent is to have the mole fraction. So I'd like to show you in an example how to convert mass fractions that are given into mole fractions that perhaps you need as part of the problem. So it is very common in engineering problem solving that you've got a mixture of ideal gases. For somehow you've determined the mass fractions and the kilograms of each constituent in the mixture. But within the problem, you're going to need to determine the partial pressure of each constituent. Very common to do that. And I'd like to show you in a pretty simple example how to convert given mass fractions into mole fractions, which is what you need. And so this is going to be really an example 12.2 right out of your textbook. It says a closed system is comprised of three ideal gases consisting of 6 kilograms of carbon dioxide, 3.5 kilograms of carbon monoxide, and 2.5 kilograms of oxygen. So do you see where if with the kilograms given, all you got to do is add up the total number of kilograms, and that will give you the mass fraction of each constituent. But for some reason, you need to determine some partial pressures. And so you need to determine the mole fractions in order to get the partial pressure of each constituent. Okay, and so here we go. It looks like I've already talked about this slide, haven't I? The mass fractions are really fully disclosed, even though they're not specifically calculated for you. So the mass fraction MF of the CO2 is 0.5. The mass fraction of the carbon monoxide is 0.292, and the mass fraction of the oxygen is 0.208 because we've got a total of 12 kilograms of mixture. So that part was easy, wasn't it? Okay, next part, how do we figure out the mass fractions, the mole fractions, now that we have the mass fractions? Again, it's going to be the same drill as going the other way. You're going to set up a table with pencil and paper. I want you to write down the column headings, the constituent, and you just write those down. The mass fractions, well, you just figured those out with units of kilograms of constituent per kilogram of mixture. So write down those units too, kilograms per kilogram of mixture, 0.5, 0.292, 0.208. Okay. Then you're going to write down the molecular weights that you should be able to get right off top of your head. You'll write those down in that column. And the units are going to be kilograms per kilomole, kilograms of constituent per kilomole of mixture. Okay? Kilograms per kilomole. The next column is going to be kilomoles of each constituent in 1 kilogram of mixture. I'll show you how to populate that in a second. And then finally, what we're praying for is the mole fraction Y sub I. It's dimensionless. Okay, next step. Let's tabulate our molecular weight, CO2, 44. Hopefully you've got that in your head by now. It's going to be 12 carbon plus 2 times 32, 44. Carbon monoxide, 12 plus 16, 28. Oxygen, 2 times 16. Plop those down. Don't just keep those up in your head. Plop those down because this is a little bit harder. The kilomoles in 1 kilogram of mixture. So what you're going to do to get your units straight, let's see, kilograms per kilogram of mixture divided by kilograms per kilomole. You're going to have to, you see that you can sort of study this to see that's why you've got to divide this number by 44. this number by 0.28 to get your unit straight. Kilomoles in 1 kilogram of mixture. So we've got 0.5 divided by 44, 0.292 divided by 28, 0.208 divided by 32 to get kilomoles in 1 kilogram of mixture. All right, so we'll do the math. We've got this many kilomoles in 1 kilogram of mixture. Well, let's add these up to figure out how many kilomoles of mixture we have. We've got 0.0283 kilomoles of our mixture. That's the sum of all the kilomoles of each constituent. So it's a small number. We add those up, add this column up. Well, now do you see the mole fraction is easy? We're simply going to take this number divided by the total number of kilomoles, this number divided by total number of kilomoles, this number divided by total number of kilomoles, and that's what's going to enable us to populate what we're looking for, the mole fraction Y sub I. I got to tell you that I cannot possibly do this in my head without writing this down. So, word to the wise, invest the time to write down this little table rather than thinking you can do this in your head. So there we go. The mole fraction, we do the math calculator. The mole fraction is 0.402 for the carbon dioxide, 0.368 for the carbon monoxide, and 0.23 for the oxygen. Okay, and so we've just been through the drill, setting up the table to go from mass fraction given to mole fraction, what we need and why would we need that other than simply being assigned. Let's say we're looking for the partial pressure of each constituent. And let's see, we can check our work. We can add up this column to see that the mass fraction adds up to 1.0, and we'll add up this column to see that the mole fractions add up to 1.0. I think we can give ourselves a big check mark, and also observe that the mole fractions do not equal the mass fraction. Common undergraduate student assumption that the mass fraction and the mole fraction are the same numbers. Okay, now in the last two videos, I hope I've showed you how to go from mass fraction to mole fraction. Similarly, mole fraction to mass fraction. Hope that helps, because that's going to be really sort of a starting point of your problem solving in Chapter 12.